very much. Let us recall what we started with last time. So we started Donsker-Varadhan theory. So it is about, well, we will be talking about multiple focuses in a compact metric space. So we pick the metric space X, and we consider multiple process xk dx. So xk is target, dx is the value of probability measures. And you know by pk x gamma the transition function, which means that this is the probability that the process starting from the point x belongs to the set gamma and k. So this is the probability that xk belongs to gamma under the law of dx. And we always assume that this is a parallel process, parallel continuous, which means that well, there are several forms. So that you can read in different values. You can say, for instance, that the function which takes x to p1 x dot. So this is the map from x to the space of probability measures on x is continuous, and this space is of course another big start topology. So this continues. This is the condition. Then we introduce the corresponding Markov semigroups. Pk, which acts in the space of continuous functions, and it is a integral operator of the kernel pk. So this is pkf the point x. Well, it has the meaning that this is the mean value under the probability px of f of xk, and can be written with the allocation function. This is integral over x pk x dy f of y, and there is also the group pk star, which acts in the space of probability measures, and so we could check that this will have the form pk star mu, we calculate set gamma. So this is the law of the process, the initial law mu, but I will not go into details. I will just write the formula integral over x pk x gamma mu of dx. And these are the Markov semigroups associated with our Markov process. And then we consider the empirical measures mu n, which is 1 over n, the sum k from 1 to n delta xk. So delta y is there as the point y. So what we get is a px value random variable. So for each, we have a randomness here because xk is a random process, we have a randomness here. So for each realization of the process, we get a measure. So this is a px value random variable. And the question we wanted to study is the validity of LDE under the law of px. So question. Now we already hold for mu n for mu n under the law. So it's a mu n under the law px. X is any initial point. So this is the question we want to study. Well, we want to apply what we developed before, Kiefer theorem. And for Kiefer theorem, we had two hypotheses. The first one is existence of pressure. What it means that for some functions, well, it depends on the function b. If it's a function b, which is continuous, and I consider the following limit. Q of b is, by definition, the limit again go to infinity of 1 over n logarithm the mean value independent on x. So very soon it will not be dependent on x, but I probably take it dependent on x. And then I have here exponential and b, this function, integrated with respect to this measure given. So the first hypothesis is that this limit should exist for sufficiently large class of functions b. Now we have a new n which has this concrete form. Well, it's not difficult to calculate that b nu n. We just integrate the function b against the sum of Dirac masses. So what we get is b x1 plus b xn. So that this mean value can be written in a different form. Ex exponential n b nu n can be written using another semigroup, which I denote by p and b. So this is p and b applied to the function identical equal to 1 and calculated at the point x. So what is p and b? P and b applied to the function f is just the same expression, except that I need to put here the function f. So this is the mean value of exponential b x1 plus b xn and f of xn. And I announced last time, without giving details on the proof, which you can easily check using the Markov property, that this is nothing else but p1b to the power n applied to the function f at the point x. In other words, this p and b, this kind of maps, form a semigroup. P and b is a semigroup with generator equal to p1b. Now let us remember that p on b applied to fx is an integral operator with the kernel px dy exponential of v of y f of y, right? So this is the same formula. When I take n equal to 1, so I have only exponential of v x1 f x1, and then I can use the law of the random variable x1 to rewrite this integral as an integral over the plane space x. Okay, so this was our setting. So this condition about the existence of limit is related to large time behavior of the semigroup PVN. Yeah.
One question about this limit, this main pressure, does it have any?
Well, it comes from statistical mechanics, but I really have the possibility to give more details about that. Okay. Yeah. Right. So the first hypothesis in Kiefer's theorem was existence of this limit for a sufficiently large class of function b. Now, this suggests that this is somehow related to the large time behavior of the semigroup, right? Because we need to take the logarithm, divide by n, and pass to the limit. So, not surprisingly, we need to impose some conditions on this semigroup, and this is the main hypothesis I'm going to impose now. It is the existence of leading eigenvalue. Leading eigenvalue. I've already formulated it last time. So there is a dense vector space so this is a dense vector space such that for any b in this vector space, not arbitrary, in this vector space, P1b has a leading eigenvalue. P1b as a leading eigenvalue. What does it mean is the following. There is a number lambda v positive. There is a function hv, which is continuous and positive everywhere. When I write like this, hv greater than 0, it means that it is positive everywhere. Such that P1v applied to hv is equal to lambda v hv. So this is an eigenvector of P1v with eigenvalue lambda v. And there is a measure which I denote by mu v, such that we have the following. For any f, a continuous function of Cx, you have the following asymptotic behavior. I take lambda v minus n, p n v, so I take my semigroup, I apply it to f, and I divide by this eigenvalue lambda v power minus n. Then this should converge to the following expression. I take the integral of f with respect to this measure mu v, and I multiply by hv. So you have a function defined in x, and it should converge to another function. Convergence should be true in L infinity norm, in Cx. So I take this function minus this function. I take the absolute value and the maximum. This maximum should go to 0 as n goes to infinity. And so this is the main hypothesis which will impose on the process. And then the theorem says that this is in fact enough. The theorem, this is the one of the version of Donsker-Varadhan theorem. So their series of paper will contain a much more than this. Now here is the exact formulation. Let further Markov process, which I denote by xk dx, besides that, this condition LE false. Okay, so there is an aspect of space for which you have this asymptotic behavior for this semigroup. By the way, I forgot to say that this is called Feynman-Kac semigroup. The Feynman-Kac. Given a continuous function b, we define this and call it Feynman-Kac semigroup. So the hypothesis is the following. So further continuous Markov process exk dx is such that this condition is satisfied. Then for any x, so I take any initial measure by initial condition, for any x, the sequence mu n, so we get the definition of mu n. This is the empirical measure of the trajectory. Well, I can consider with any measure of px, the procedure under px. Satisfies the LDD with the rate function which is the following form. So rate function should be a function from px, because we are aiming in px very random level, with ranging 0 plus infinity. So here's how it can be written. I of nu equal to the supremum with respect to all b greater than 0. I take the logarithm b divided by pnb. Pn is the Markov semigroup, and I integrate this with respect to the measure b. So this is the Donsker-Varadhan theorem. for any initial condition x, the empirical measures satisfy the large deviation principle linear rate function I. And I'm going to prove this result. Now, so the problem for today is to prove this result. Then we need this condition to understand what are the what this condition is about and for which processes this is satisfied. And then finally try to see what kind of initial equation this can be applied. Yeah.
What was the mu and the
rate function? Rate function mu is a measure of x, right? So we are dealing with random variables in range in px. This was what was before x calligraphic, right? So we have clearly an x calligraphic, which is a compact metric space. Now I have a complete compact metric space. I have another compact metric space, which I denote by x, and I consider px, the space of probability measures, with a restart topology. It is again compact. So I have a random variable with range in here. So if I dealing with LVP for this random variables, the rate function, which will be function from here to 0 plus infinity. Okay. Well, there are two conditions in Kiefer's theorem. So idea is to apply Kiefer's theorem. Yeah.
What does that mean? P1b in the rate function?
P1b is exactly this. PKF is contain the transition function of type 1 and you integrate f.
The Markov symbol.
Exactly. This is the Markov symbol of type 1.
This is B is the function, continuous function.
Yeah, because sorry, I forgot to mention B is positive and I assume that B is continuous. Yeah, I take all the continuous functions which are positive, and I take the logarithm of B over P1B. X is complex. X is a compact space, so if the function of positive is positive, then it is strictly positive point. Every point is positive. Continuous, therefore, it is separated from 0, so there is no problem in division by P1B. Okay. Right, so proof, we need to check the hypothesis of Kiefer's theorem. Okay, so step 1. Kiefer's theorem starts with pressure, so let's look at the pressure. So what we need the existence of this limit for V in a dense vector space, and my dense vector space is there. So I take V calligraphic, and I take this expression. Qxv is equal to, I take the formula which is there. So I have the limit as n goes to infinity, 1 over n, logarithm, and I have here p and b applied to the function identical equal to 1, calculated at the point x. But now I have a lot of information about this, right? Because I have this asymptotic convergence. So I can rewrite this in the following form. Limit n goes to infinity, 1 over n, logarithm. Let me add here lambda n b to minus n to be able to pass the limit. Lambda b to minus n, p and b applied 1. So let me not write this point x, it will be always in the point x. Then I change something. I added here to lambda b to minus n, which is a constant. But to make sure that nothing changed, I need to subtract this term. But when I take the logarithm lambda b minus n, this minus n comes here, it becomes minus logarithm lambda bn. So I need to add logarithm lambda b. Then I record. Right, so I didn't change anything, I just wrote the lambda b minus n to be able to apply this formula. And then I added the logarithm of lambda b to make sure that this is positive. But now this sequence converges uniformly to positive function multiplied by 1, because now my function f is equal to 1. I take integral of 1 with respect to mu v, but this is a probability measure, so I get 1 here, multiplied by HV. So this converges to HV. So you have a uniform conversion to HV, which is positive everywhere. I take the logarithm and find a number. I divide by n and pass the limit. So this term will disappear. So this one converges to 0. And I'm left with only logarithm of lambda n. Is equal to logarithm of lambda n and lambda v. Right? So the existence of QV for any v is a simple consequence of this hypothesis. So the first condition in different theorem is satisfied. Now I need to understand if the second condition is satisfied. But before doing so, let us try to see if we can say something more about rate function. Step 2, rate function. Basically, what I want to do is just to show that this formula is true. Kiefer's theorem says that under some hypothesis, which I still need to check the second part, you have LDP with the following rate function. I of nu is equal to the supremum, and v is in Cx, the integral of v with respect to mu minus qv. So for the one, this is quite different from what we have here. However, let us recall that we established the following property for the function q. We know that q v plus c is equal to qv plus c. So this is true for any v in V calligraphic and for any c in R. When I write c here, I mean a function which is identically equal to c. So if I add c to the function v in this definition, I will just have plus c everywhere there. So I will just c to power n, which I will have. Okay, let's check this. So q v plus c. What it is the limit of when n goes to infinity, 1 over n logarithm, and I have this expression, right? N v mu n. So now I have mean value exponential n v plus c mu n. But when I evaluate this constant c against mu n, I get just c. So what is written here is just exponential n, there is no n, exponential c, no, there is n. Because this is a problem together. So there will be n multiplied by c, and then mean value exponential n v integrated with respect to mu n. But this is a constant. When I take the logarithm divided by n, I get just constant c. So obviously we get qb plus c. Okay, so when I add a number c here and here, nothing changes. So all this to say that v plus c mu minus q v plus c is the same as v mu minus q of v. So I need to take supreme over all functions. But I'm saying here that if I add a constant c to this function, then nothing changes. And therefore, when I take the supremum, I can take only those functions for which this q of v is equal to 0. Let me write it and let's see why this is true. So instead of taking supremum with respect to all functions, I can take the supremum with respect to all functions on x such that q of v why? Because if I take one function v here, which does not satisfy this condition, I can add a constant c, which will be minus q of v, to have this condition satisfied, and this will not change anything, because this expression does not change when I add c to the function v. So I have convinced you that instead of considering this formula, I can consider the supremum over all functions for which q of v is equal to 0. Now the question is how to find such function. The fact that we have exponentials of phi suggests that probably it's a good idea to take off logarithm of something. And then after some calculations, you can easily convince yourself that a good idea is to consider the following function. V, which is equal to logarithm W divided by P1W. So in fact, I'm claiming that V can be represented in this form if and only if QV is equal to 0. Okay, so this is a small lemma which I will prove. Let's take this lemma for granted and let's see what it gives. So it gives the following: that I of Q, yeah, this is can be represented in this form with some W strictly positive. V was arbitrary, but W is strictly positive. The thing is that function B can be represented in this form. It's a W positive if and only if Q of P is equal to 0. Okay, so that if this is true, then I can rewrite that formula in the following form. This is the supremum of W strictly positive. Now I don't need to specify anything. And instead of B, I need to put the logarithm of logarithm W divided by P1 W and integrate it with respect to B. And this is exactly what is written in the theorem. So if I can prove that the function B is representable in this form, if and only if Q of P is equal to 0, then we are done. Because I have this variational formula, I have Q equal to supremum over B with QB equal to 0. But this is the same as this formula if we can prove this representation. So let's put the number here, the proof of 1. Okay, let's assume that B is representable this form. Let's see why Q of B should be equal to 0. So what was our Q of B? It was limit of certain limit. So let's write this in more details. Ex exponential Vx1 Vxn. Right? So I need to calculate this. But if V is written in this form, what I get is the following: in value Wx1 divided by P1 Wx1 Wxn divided by P1 Wxn. Right, so I need to calculate this in value. So W is a continuous function or a compact metric space, which is positive. Therefore, I can find the number C that is smaller than C and greater than C minus 1. So let us bound this expression from above and from below. What I need to bound it from above. Sorry, this is W minus. Right, so I want to bound it from above, for instance. To do this, I mark that if W is greater than C minus 1, then P1W will be also greater than C minus 1, because P1 is a probability measure. Right, so I integrate W with respect to the probability measure. If it is bounded by C minus 1, then P1W, which, okay, let me try it just to be sure that so it's everyone. P1 X dy W of y. If this is greater than C minus 1, then I can put it here, and this is the probability measure I get 1. So this is greater than C minus 1. Therefore, if I replace here by C minus 1, I get something which is bigger. So this is smaller than EX. So let me write differently. Let me denote this expression by Gn. So this is the Gn. So I will have Gn minus 1 WXN and multiply this by C minus 1. This I didn't change anything. I just said that this one is called as C minus 1. I kept WXN, and what is that? Is G A minus 1. So J is A minus 1, depending on where we think from X1 to Xn minus 1. So what it is, I apply our property, C minus 1, here. Then I write that this is the same as mean value with respect to Tx. This, I want to take conditional expectation with respect to F A minus 1, so I can put this in front. And I have expectation of WXN when we know everything up to the point A minus 1. That's right. I 1 over P1W by C minus 1, and I do the conditional expectation. But the Markov property says that this is the same as I need to take the difference of times P1, apply to W, and take to the point and at the point X A minus 1. And now it becomes clear what the idea is. Now I have the
C instead of C minus.
yeah, you're right, it's C. Because C minus 1 here, but now it's in the numerator, so it's C minus 1, A is C. So what we have here is the following: C expectation G A minus 1 was WX1 P1 WX1, the product up to WX A minus 1 P1 WX A minus 1. And I have here P1 WX A minus 1. Right? So this is G minus 1, this is the third term. These two terms as well, and what I get is the same expression here, except that A is replaced by A minus 1. And there is no additional constant here. So everything will cancel out, but this one. This is the same as C Tx WX1, but this is the function, right? So we want to make this. So this is the C P1W at the point x1, at the point x. So this is this expression, right? What I need to do with this, I need to take the logarithm, divide by n and pass to the limit. But when I do all this, I have just a constant function. Therefore, Q of B will be equal to 0. This I prove that if B can be represented in this form, then QB is equal to 0. Now let's prove the implication in the opposite direction. Right, so I want to prove that if Q of B is equal to 0, then I can find a function W for which B can be represented in that form. Let us remind that Q being equal to 0, it is the same as saying that lambda B is equal to 1, because my Q of B is the logarithm of lambda B. Q of B equal to 0 means that lambda B is equal to 1. Now let us try to see what this function W should be. If B is equal to logarithm W divided by E and W, then I can take the exponential multiplied by P1 to get a representation for W. W will be exponential of B, right? I keep the exponential, and I multiply by P1 W. And then I have W here. Let's put this W into here. What we get is exponential B, P1, and then the same expression, exponential B, P1 W. But P1 exponential B, it is exactly P1B. So what I get is exponential B, P1B, and then apply it to P1W. Let's put again, instead of W, let's put again this expression. What we get is exponential B, then P1B, then P1 exponential B, P1W. These two form again P1B. what we get here is exponential v, e to v, P1V, P1V, this is a semigroup by E2V, and I have here P1W. And so if I continue this process, I can get exponential V, E and V, and apply it to P1W. Let's recall what we are doing. We say that we want to find the function W such that this is true. So if this is true, then this should be true. So, but now I can use this fact that we have this condition on the leading eigenvalue. This should converge because now the v is equal to 1. There is no factor here. So this should converge to the exponential v, doesn't change. Then you can take P1W integrate with respect to uv and put here hv. Right? So this is a constant. It does not play a role because I can multiply W by constant, nothing will change. This suggests that W can be written as exponential VHV. So this is our conjecture that if I take W equal exponential VHV, then everything will be fine. And indeed, if you put it here, what we get? We get logarithm. We get logarithm exponential VHV. And then Pn, P1 exponential VHV. But this is exactly lambda VHV because lambda V here H is the eigenvalue of P1V. What we get is logarithm exponential VHV divided by lambda VHV. But lambda V is equal to 1. I can simply divide by HV and I get exactly V. For this I prove this equivalence, and therefore I have now the formula for my rate function. And now the last step, in fact, this is the crucial point. Step 3. Equilibrium state. Uniqueness of equilibrium state, right? I need to check the uniqueness of equilibrium state. Let us recall what it is about. So I want to prove that for any V is mechanographic, there is a unique equilibrium state, which means that the equation Q of V equal to V mu minus I mu has a unique solution. Okay, so this is the condition, second hypothesis in Hilbert theorem. For any V in this space mechanographic, the equation has this equation. So we know that Q of V is the supremum of this. So I want this supremum to be saturated at the point Q. So uniqueness of equilibrium state says that this equation has only one solution. Now let's begin with the following particular case. Let's assume that V is equal to 0. Okay, so I begin with a particular case when V is equal to 0.
In the previous step, we could just take W equal to EVHD and say that this is until here you are explain how you go there.
Yeah, that's the
Yeah, this is the explanation of.
So let's continue the case then V is equal to 0. Then what does it mean uniqueness of equilibrium state? It means that I of mu equal to 0, because V is 0, this term disappears. Q of 0, when you take V equal to 0, you just have a multiple group and obviously it converges to 0. So I need to show that I of equal to 0 has a unique solution. Okay, so let's see what it means that I mu is equal to 0. I suppose that mu is the solution of this equation. Let's see what it means. Now I have a formula for this. So I mu is given by that formula. Let's remind that when W is equal to 1, then the supremum, sorry, not supremum. There is no supremum if W equals 1. logarithm W P1 W U is equal to 0, right? If I take here 1, I have 1 divided by 1, which is 1. I have 0 integrated with respect to mu, so this is equal to 0. So the function W equal to 1, I have this supremum saturated. If I of u is equal to what? 0. So if I of u is equal to 0, then this relation is true for W equal to 1. But then this means that if I take any other function, in particular function which are close to W, then I need to have something smaller than 0. So this implies that for any u, Cx, the function f epsilon, which is exactly this, propagated by epsilon u. So I have normally 1 plus epsilon u divided by p1, 1 plus epsilon u, and integrated with respect to u. Okay, so I take perturbation of the function equal to 1 on this supremum saturated. So if I of u is equal to 0, then for any other function, this can only be greater than 0. So this function has a local maximum of 0. Right? So the fact that I of u is equal to 0 implies that this function has a local maximum of 0. In general, this is not true if I of u is greater than 0. But if it is 0, at the point the function 1, you have 0, and therefore for any other function close to 1, it is smaller than the value of epsilon equal to 0. So now let's write the necessary condition for the local maximum. So let's take derivative of f of epsilon when epsilon equal to 0. So what we get, okay, so this is the derivative when epsilon equal to 0. Let us evolve the logarithm. We have logarithm 1 plus epsilon u minus p1 applied to 1 is 1. So I get logarithm 1 plus p1u epsilon p1u and integrated with respect to u. Okay, so this should be equal to 0. Let me start. So this is equal to 0. But this is easy to differentiate, right? So we have 1 over this, and then I take epsilon equal to 0, I get just 1. And then when I differentiate this, I get u. So this means that it is u integrated with respect to u. And for exactly the same reason, here I get p1u integrated with respect to u. Okay, so the conclusion is that for any u in Cx, well, I can put p1 of the measure mu because these are real fields. What I get in the following u integrated with respect to mu minus p1 star mu is equal to 0. So I have a sign measure such that the integral with respect to any continuous function is equal to 0. It is well known that this implies that this measure is equal to 0. Mu is equal to p1 star mu. Which means that mu should be a fixed point for the semigroup p1 star. But I claim that this is the only this measure mu. Now I can use again this leading eigenvalue hypothesis. The claim is that so this is true for any b. In particular, this is true for b equal to 0. When b equal to 0, lambda b is equal to 0. So what I get is the following, that p1 applied to f should converge to some measure f mu, let's write f mu 0, This is the function corresponding. This is the measure corresponding to function b equal to 0 multiplied by function identical equal to 1. Okay, so that hypothesis is not really guiding. When b is equal to 0, it's easy to see that it gives this lambda 0 is equal to 1. So in particular, I claim that this implies that this mu0 is the only eigenvalue of P1 star. Indeed, if P1 star mu is equal to mu, then Pn star mu again is equal to mu, and then for any f, I can write f Pn star mu is equal to f mu. Therefore, I can put Pn star of f is equal to f mu. But now, when I ask to the limit as n goes to infinity, what I get here, Pnf, it converts to this one. So it converges to f mu naught multiplied by a function identical equal to 1 and integrated with respect to another volume in every. And this is equal to f mu. But mu, well, this is a constant I can put in front of the integral. Mu against f1 gives you 1 because this is a probability measure. So what we get is that for any f in x, we have f mu naught equal to f mu. And therefore, this mu, which is an eigenvector for P1 star, should be equal exactly to mu naught, which comes from the leading eigenvalue hypothesis. Okay, so let us summarize what we need. We wanted to prove that this equation, for any b in b kind bracket, has at most one solution. In fact, the uniqueness is an issue. And we can see the first particular case that b is equal to 0. So when b is equal to 0, these two terms disappear, and we get the equation I is equal to 0. We want to prove that this equation has only one solution. Claiming that that solution is precisely the measure mu, which corresponds to function b equal to 0 in that hypothesis. And what we need here is exactly this. So we know now our rate function can be given in that formula. If I of p is equal to 0, then this function will have a local maximum epsilon equal to 0. We roll this necessary condition of the local maximum, the limit is equal to 0. We calculate it, and we saw that if you satisfy this equation, then necessarily it is an eigenvector for the Markov operator P1 star. And that Markov operator P1 star, due to that condition, the stability condition of the Feynman-Kac semigroup, is only one eigenvector, which is that function, that measure mu. Okay, so this is the case, this is the particular case when b is equal to 0. So we don't have time to go to see all the details when b is arbitrary. But nevertheless, let us write the formula to see that it is not that different.
One question.
Sure.
For showing that the rate function is of this form, if it exists, did you use already all the assumptions of theorem or?
Yeah, the fact that just 1 second, the fact that I of mu has this form, I think it used somewhere, or maybe, yeah, I already saw that. But in fact, we can do something more. In one direction, one inequality is always true. The other one, this one, yeah, but I'm afraid, you need some converse. You need converse in order you can get only inequality. If you don't have the leading eigenvalue assumption, you will get only inequality. Okay, so we want to prove that this is true, the same is true for any b which is in the carried out. So what we want to prove, we want to prove that this equation, I of nu, equal to, let us write in the following form, b nu minus qb as a unique solution. But what is I of nu? I of nu, well, it is that, but also let's write as a legitimate transform of q. This is the supremum when w belongs to Cx of w mu minus q of w. This should be equal to b mu. Now this is right minus qb. Well, let's put this under the sign of supremum. So what we get is the following: the supremum w in Cx. I will have w minus v integrated with respect to u minus qw minus qv. And this supremum is equal to 0. And now taking supremum w in Cx and considering w minus v is the same as considering again all the w. If I replace this by another function w, then I can rewrite this expression in the following form: the supremum w in Cx. Here I have w integrated with respect to u. So let me write in w prime. Now minus, I need to replace w, v is fixed. I need to replace this w, I need to express this w in terms of w prime. This means that w is equal to w prime plus v. And q v plus w minus qv. And then this is equal to 0. But what we got is very similar to this condition. I of q is equal to 0. So if I can manage to show that this is a pressure function for another semigroup for which I have this leading eigenvalue condition, then they are done. If this is a pressure for another Markovian semigroup, then exactly the same hypothesis applied to this other Markovian semigroup will give you uniqueness of the ring function. So this is the main idea. Now, if you look for a few minutes or 2 hours on that expression, you can guess what this Markovian semigroup is. So let me write that Markovian semigroup, and I will not continue really because we don't have much time. So that Markovian semigroup will depend on B. The Markovian semigroup for which this will be true is the one that is noted by R1, is the one generated by the following one, R1 will be lambda v minus 1, hv minus 1, and then we have T1v applied to hv, right? Okay, the claim is that this is the Markovian semigroup. It means that it is given by a kernel, positive kernel, and preserve the function identity equal to 1. Let's check, for instance, that R1 of 1 is equal to 1. R1 applied to the function identity equal to 1, what it gives? I can put, if I put 1 here, you have T1v applied to HV, so what you get is lambda v minus 1, HV minus 1, and T1v applied to HV, this is exactly lambda v HV. Everything cancels out, and you get the function identity equal to 1. So it is not difficult to show that, well, now we need to consider R1 W. So the claim is that this claim, which I will not prove, if you take the limit as n goes to infinity, exactly the same expression as we did for p. On over n, over it, now instead of p I take r, and now I have a function w, exactly the same way I just constructed p1b from p1, we construct r1w from r1, and apply it to the function 1, and I take any point x. Then the claim is that we will get exactly this expression, q b plus w minus qb. And let me note this by q b of w. Okay, so you want to prove that this equation has a unique solution u. The idea is to reduce this to the previous one, and b is equal to 0. And b is equal to 0, you have this expression, this one, yeah, I is equal to 0. And then this simple argument combined with the hypothesis gave you the uniqueness. Now the idea is to represent this as a pressure for another Markovian semigroup. The claim is that this is the semigroup unique. You take the iteration of this one, you do the calculation, you get exactly this expression. So this will be unique unique point 0 for this new function I, and this will complete the proof. Okay, so I hope I convinced you that it is not that different from the previous one if you have that very divergent condition. Well, now let's the natural question is to understand when this condition is satisfied. Okay, so let me summarize what we have done. So we have this this theorem of Donsker-Varadhan, which says that if your Markov process is such that for V in a dense subspace, the Feynman-Kac semigroup has a leading eigenvalue, then you have large deviation principle for empirical measures and this expression for the rate function. Now I want to understand when this is satisfied. So the next small chapter is the Feynman-Kac theorem. And let us begin with an example of precisely the Feynman-Kac theorem. Example. So I consider the case when X is a finite space. X1, Xn is a discrete metric. The distance between Xi and Xj is equal to 1 minus delta Ij. Right? So in this case, we have a finite state Markov chain. Finite state Markov chain. So if I have a function x, then I can represent it as a vector, right? I can write the vector f1, fn. I can even consider it as a vector column. When fj will be the value of f, the point fj. If I have a measure, then again I can represent it as another vector. Now mu j will be just the measure mu, the mu measure of the point fj. Now, how do we write a transition function in this case, or a Markov set of this case? It's just a matrix, right? So P1 5 to F, 5 to F is just Pij Fj. From 1 to n, when Pij is the probability of transition from the state xi to the state to the set xj. Okay, so this is the P1 f at the point xi. Here I can identify my Markov process with the powers of this matrix P. So Pn is just P power n, when this P is a matrix consisting of those elements. Pij. All of them are positive or zero, right? And the question is, well, this is Markov semigroup. If you have Feynman-Kac semigroup, what you need to do is to multiply P, let's write P1B. What it is, I need to multiply by exponential of B at the point xj, right? So this will be matrix with elements Pij exponential of, let's write Bj. Right? The difference between these two is that this one is stochastic matrix. The sum of Pij is equal to 0, equal to 1. The sum of Pij is equal to 1. And this one is not. If I take the sum with respect to j, I do not necessarily have 1. And there is a result called the Donsker-Varadhan theorem, which gives you sufficient condition for having leading eigenvalue in these two different situations. In the case of stochastic matrices and in the case of positive matrices. So the theorem is the following. Theorem is the following. This is Donsker-Varadhan's theorem. Donsker-Varadhan's theorem. It says the following. The first case, let P is a stochastic matrix. Stochastic matrix means matrix with non-negative entries with a sum equal to 1. On each line, the sum is equal to 1. P is a stochastic matrix such that there is J naught in one end. The index J naught. And there is an integer n such that the transition from any state I to the state J naught time n is strictly positive. Okay, I can single out the state such that if I wait the infinite long time, then transition from any state to that one will happen with positive probability. Then P now leading eigenvalue necessary 1, then lambda equal to 1 is a leading eigenvalue for P. And there is a second part of the theorem. Which says that in the general case, so let P be a matrix with non-negative entries. Such that there is an integer n for which, for any ij in 1n, Pijn is strictly positive. Then P as a leading eigenvalue. So in the case when X is a finite space, the Frobenius theorem gives you sufficient. Well, they are not necessary. You can easily look up examples, maybe it doesn't work, but reasonable sufficient conditions for the existence of eigenvalues. In fact, the second case can be reduced to case A with a simple change of matrix, which is somehow similar to that one. But I will not go into details. Now it turns out that in the case of compact matrix spaces, you need something more, but not much, to have the existence of leading eigenvalue. So here is the result, which I will not prove when trying to maybe not even give you some ideas because we don't have much time. Okay, so I will formulate it in abstract terms. So it's fix a function q which depends on x and gamma. Right, so x is a point in a compact metric space X. Gamma is a set in Borel sigma algebra matrix. And I assume that, well, you need some natural conditions. You need that the function, when you fix gamma, you have a function which is measurable. It's Borel measurable. Or any gamma. If you fix gamma, now if you fix x, you have a probability measure. So gamma, you fix gamma. Sorry, it's a positive measure, not probability. Okay, so if you consider a map which goes from Borel sigma algebra to R, this should be positive function, which is a measure on the Borel sigma algebra. And also I assume that it satisfies the Fellow's property, meaning that this map is not only measurable but continuous. But anyway, so the condition I will impose are much stronger. So with this Q, I can associate the semigroups. So I denote by Qn the semigroup generated by Q, which acts in the space of continuous functions by exactly the same formula as a Markov semigroup. To f at the point x is equal to integral over x to x dy f of y. And here is the theorem. Let inside that the following two conditions are satisfied. The first one is strong irreducibility. And it's exactly the same condition as here, but it should be written now in terms of transition from a point to a goal. So for any R, there is delta, and there is M such that transition, well, it's not a real transition because it's not an atomic number, but Q M from X to the goal around Y of radius R is greater than delta. And this should be true for any X and Y in X. Yes, I fix the point, I fix the goal, I fix the radius, right? So we are in a compact metric space. I fix the radius R. Then, if M is sufficiently large, then QMX, this goal is greater than delta. So this delta is universal, it does not depend on X and Y. Okay, QM is what you get after iteration. So this is the same as the semigroup applied to the goal BYR and calculated to the point X. Exactly as in the Markov expression. So this first condition is the analog of this strong irreducibility condition for matrices. Okay. Now the second condition is uniform strong color. For that I need total variation metric. Well, here let me first write and then we'll discuss. So the function which takes X to Qx dot. So this is a function from the space metric space X to the space of positive measures, and I consider it to be the total variation metric. It should be continuous. Okay, so for each X, this is a measure, this is a positive measure. So it belongs to M plus X. So these are positive measures on the space X, not necessarily probability measures. I consider it the total variation metric. What is the total variation metric? So if you take two elements, mu1, mu2, the total variation, for instance, we can define as the supremum over all functions f, which are bounded by 1, f mu1 minus f mu2. Well, usually I write here 1/2 to make sure that on probability measures you have maximum distance equal to 1. Okay, so this function should be continuous from X to this space, which is a Banach space. This is a normal fact. So if you have these two conditions, here is strong irreducibility and uniform strong color. Why uniform strong color? Because it is really much stronger than the Feynman property. We don't have time to discuss it in more detail, but it says that if you take any measurable function, then the function QF will be continuous. And in fact, much more than that, we have some uniformity with respect to the functions, in the unit model. Or you can write it in a different form because you have a continuous function on a compact space with range in a Banach space, you have uniform continuity, which means that if you take the limit, so this is the same as saying that the limit when delta goes to 0, and you take the supremum for a point whose distance is smaller than delta, and you compare Qx1 with Qx2 in total variation metric, then this should be 0. Okay, the two hypotheses: strong irreducibility, but we now have metric space. You need some regularity condition on this transition function Q. Then Q has a leading eigenvalue. Well, the proof of this theorem is far-reaching generalization of the Rho-Frobenius theorem. Basically, what you do, you first consider the stochastic case and prove that under a condition which is similar to this one, which means that you need only one point to which you can go, and under condition which is bigger than this one, you have unique fixed point, you have a contraction, and therefore you have a leading eigenvalue. And then, as in the case of the Rho-Frobenius, you make a change, a small change of matrix to reduce the general case to the stochastic case. Okay, so this is the result. And now, how to apply this to our situation? The application for the Donsker-Varadhan. Well, what we want to do is to apply this theorem to the Feynman-Kac group associated with Markov process. But it's really not difficult to see that if you have these two hypotheses for the transition function, then you will have exactly the same thing for the Feynman-Kac group. Right? So remember, if I and uniform strong color are true for P x gamma, then they are true for P B x gamma. Why? Because here it is about transition, right? And this PV difference is that you just multiply by a function exponential b. So if the transition is positive, then it remains positive. And the same here. If you have continuity after multiplying by a continuous function, nothing changes. So the conclusion is that corollary, if the transition function for xk dx satisfies these two hypotheses, strong irreducibility and uniform strong failure, then the conclusion of Donsker-Varadhan is true. The DV theorem is true. Well, I guess this is all concerning the abstract theory. Right, so we have 10 minutes, so let me briefly summarize what we have done, and let's consider one example. Of course, I will not be able to give any details, but at least we will have some idea what it can be applied to. So we consider the Markov process in a compact metric space. That Markov process should satisfy two hypotheses: irreducibility. That is a quite strong hypothesis. That you are able to go from any point to any other point, and you have some uniformity in probabilities. So if you fix a radius, if you fix R, then if you wait for sufficiently long time, then the probability of transition from any point to any ball of radius R will be minorized by a positive number. And the second condition, that this transition function has some regularity. It must be uniform and strong failure, which you see it says that if you fix the initial point, you get a measure at time 1. That measure should depend continuously on x in total variation metric. Should depend continuously on total variation metric. Okay, so if you have these two properties, then you have the conclusion of Donsker-Varadhan theorem. Large negation with rate function given by this variation form. So what can be, what one can apply, which kind of system we can apply this theorem to? Now, I gave already an example. I think that I will be able to keep it, but now I will just formulate it again and specify the hypothesis you need. Application, so this last section, the short one. Application to ODEs with random divisions. As the title suggests, we need to consider an ODE. But the example I gave in the first lecture was in Rn or Rd. Now, because I want to have some compactness, I will consider on a compact manifold. Like this S, which is a compact manifold. If you don't like manifold, you can think of the surface in Rn of sufficient large dimension. And this is in fact the generalization, there are no other manifolds. You fix vector fields, V0, Vn. Again, if you are in Euclidean situation, you can think of vector fields which are tangent to your surface, and you consider following differential equation x dot equal to V0 x plus the sum L from 1 to m, the processes either L of t, V L of x. So here, eta L is a process. So we have n processes, right? So let's say eta is eta 1, eta m. This is a random process. So this is an Rn value random process, right? Because we have n scalar functions. So this is an Rn value random process. So I will assume that this random process has a special form. I will divide the time axis into intervals of length 1. And on the first interval, I will consider the first process, zeta 1, and I write the second one of this. On the second interval, I write process zeta 2, zeta 3, and so on. So I will write eta t in the following form. This is the sum, a from 1 to infinity. I take the indicator function of the interval k minus 1k of t, and I multiply the k term by the process zeta k. Zeta k, all of them, these are I, E. In, I would like to have a Hilbert space, so it will be I and D in the space E, which is by definition L2 of 0, 1 is ranging Rn. And I have zeta k, E minus k plus 1. So let's take t, which is in interval 0, 1. Then the only term which is different is when k is equal to 1, and I have here zeta 1. K is equal to 1, this disappears, and I have zeta 1. When t is between 1 and 2, the only term which is not 0 here is when k is equal to 2, like 1, 2, and here you have zeta k, zeta 2, t minus 1. Right? Again, you have t minus 1, which varies in 0, 1, and so on. So this is what up, right? So I take the process zeta 1, zeta 2, zeta 3. Now these are random variables in this space E, and I use them to hook up a new process theta t, which will drive my differential equation. Okay. In other words, if I denote my x now from x times e into x, and which takes the initial condition x naught and the process zeta to x1, xt is a solution of this one. And let me write here the initial condition: x at 0 is equal to x naught, which is 2. X is a solution of 1, 2 with eta equal to zeta. Then, if I denote by xk the value of the solution at time k, I can write that xk is s k minus 1 zeta k. In other words, I have my initial point x naught. I solve on the interval 0, 1 my differential equation with zeta 1. I get the point x1. Then, starting from x1, I solve my differential equation using zeta 2. And I get x2, and so on. So, if your force, your eta, your stochastic process has this particular structure, be it zeta 1, zeta 2, ID, random variables in E, then I get this discrete time random dynamical system, and due to independence of zeta k, I know a Markov process. So with this random dynamical system, I can associate a Markov process, xk px. Markov process. Markov process in x. So we are in a situation discussed there. We have a compactor manifold, so this compactor in space, and I have a Markov process which I cooked up using the flow of the differential equation. Now the question is, what are the sufficient conditions for application of the corollary? Well, the theorem is the following. There are two hypotheses. Suppose that they are not optimal, they are sufficient. The first one is non-degeneracy. Of vector fields. I want for any x in x the vector span of v1x, I don't take v0, v1x, vmx be exactly the tangent space of my manifold. So these vector fields can derive your solution in all possible directions. Second condition is decomposability. And non-degeneracy of the noise, driving noise. It says that these random variables, zeta k, they are random variables in L2, can be represented as a sum, some other random variables, psi kj multiplied by 2πj. Okay, from 1 to infinity. Phi j is an orthonormal basis in E, and psi jk are independent random variables, scalar random variables, independent scalar random variables. You need some conditions. You need them to have density. Positive densities. So the law of psi kj must have a density, I denote it by rho j. It should be independent of k because the zeta k are IID. So rho j of s ds. This rho j must be, for instance, you can take continuous differentiable, and they also must be positive. I think this is a kind of regularity condition for the driving noise. And concerning the decay infinity, it suffices to assume that the sum of the mean value squared is finite. K for one unit. Okay, so each DTK can be decomposed in a non-normal basis T with some coefficient, they will be random, satisfying some regularity and non-degeneracy conditions. The density should be with T1, positive element, and the sufficient with it, so that the DTK is also enough. Then the conclusion of Donsker-Varadhan is true. The large deviation for is true for this Markov process for XKPS. Now, according to Corolla, what we need to check is the irreducibility and uniform storm cover. Well, it is now just measure theory to show that if you have this non-degeneracy of the vector fields plus regularity and non-degeneracy of the noise, then the transition function given by for that Markov process will satisfy those two conditions. In fact, it is straightforward to see that the transition function P1 x gamma will be just the probability that this S x zeta 1 belongs to gamma, right? Or I can write in a different form. I can write that this measure P1 x dot is the image by the map S x is a parameter and it acts on the measure graph. Here L is the law of theta k. And the transition function is the image of this probability measure on E by this map S, which solves my differential equation. So basically, those two conditions are about the image of some non-degenerate measure, non-degenerate measure under some differential map. And it is really, I don't know, soft measure theory to check those two positions. So, first, I don't time to specify it, I will try to write it down and
and in the field of velocity, as I recall, there are some conditions like irreducibility and uniform storm error property in the paper, for example, Hermann. Are the conditions here the same?
In theory.
yeah, yeah, I mean, these are classical conditions which are now
Yeah, so the conditions imply simultaneously the the large deviation principle on the distance.
Well, ergodicity is true on the much bigger condition. I mean, you just need a small contraction somewhere, right, around the point. For ergodicity, basically what you need is that there is a ball, such that if you take any 2 points in that ball, then the total variation distance in that normalization is more than 1 minus epsilon. What I require here is much stronger. Well, this is far from being continuous, right? This is just that if the points are in a fixed ball, then there is a common part between these two measures between Tesla. Here for Donsker-Varadhan, I need really continuity of this function. I need this to go to 0 when x1 goes to x2. As I wrote there, and the supremum between this of the total variation between these two measures, I wrote it somewhere. Here it is. I have the supremum for all the points which are close to go to 0 when this delta, recognizing the closeness of the point, goes to 0. So for Donsker-Varadhan, I need much stronger property of regularity of the transition function and also for irreducibility. Then for ergodicity, I just need to be able to bring my solution to this goal. then transition to any point to that goal to be separated from zero interface for sufficiently long time. In Donsker-Varadhan, I do from anywhere to anywhere, which is much of the condition. There are results which say that you don't need that, you get you can impose something weaker, but there are fine results in the situation.
Other questions? Let's say,